design, and it has a number of things that are common to topics that we're interested in here, so I'm sure that there'll be good questions. He's a senior scientist at General Atomics, where he's been an employee for 39 years. During this time, he's been a contributor in the fission, magnetic and inertial fusion, and high-energy laser fields. At present, he is the project manager, co-inventor, and technical leader for the EM2 nuclear reactor and advanced helium-cooled conversion zone fast spectrum reactors. He has recently returned to the fission community after 20 years in other fields and is working to cross-fertilize technologies and materials from other fields and with nuclear fission. Previously, he spent 10 years developing innovative solid-state lasers and was the co-inventor of the HELEDS, if that's the right way to pronounce it, it's an acronym, high-power military laser. Prior to that work, he worked for the fusion division as an employee for the ITER Joint Central Team, where he was responsible for tokamak electrical systems. He conducted many studies on the application of nuclear energy to non-nuclear or non-electricity uses, including desalination, and developed the deep cogeneration and desalination code with for the IAEA, which is currently used in many nations to evaluate the use of nuclear power for desalination. His PhD is from Cornell University in applied physics, and he is the author or co-author of over 40 articles and papers on advanced energy production technology. Dr. Schleicher is committed to innovation and technology advancement in the energy field. He believes that the U.S. must advance substantially new and better concepts in order to have significant influence in the direction of the global nuclear economy. He believes that new ideas are key to attracting talented young minds into the nuclear field to make these technologies a reality. And again, the topic that he's going to describe today, I think, will be of direct interest, and these other areas he's worked also are of interest to us. So we look forward to the talk and the opportunity to ask questions. I'll turn things over now to Bob.
Oh, well, thank you very much. There's kind of a long-winded introduction. Yeah, I talked to a group, probably many of you here, about a year and a half ago, about a new idea that we call EM2 for energy multiplier module, and this is something that's well supported at General Atomics, and we've made some progress. And so I'll give you a little bit of update on what the design looks like since the last time. And one of the things I wanted to try to talk to you about, since all of you are probably in graduate studies, and you might be thinking about research, and when you think about research, you have to think about where are you getting funding, and this is an issue that we have to deal with in doing research at General Atomics, and for EM2, it will require a lot of development funding, and we have, as I said, been funded by our company, but we have not been successful in getting funding from the Department of Energy, for example. And so that's kind of disconcerting, so we have to look for other avenues to help support our R&D budget. And I'll talk a little bit about how we spin some of the technologies into other areas to seek other sources of funding and then get the whole job done. And that's something you all need to think about when you go into research, and that is how can you be clever enough, not just a good idea, but versatile enough to get funding. And so we'll touch a little bit on that. So anyways, this is an EM2 update, and we'll talk about it. Maybe just by way of introduction, what today are the key issues that are confronting nuclear power? Well, the nuclear renaissance, I mean, that was fading already in 2009. The major issue there is the high cost of the escalating cost of construction of nuclear power. And in about 2010, the DOE reported that new nuclear construction cost around $5,300 a kilowatt installed. That's quite a bit. And when you work that out into the price of power, that is in the neighborhood of 10 cents per kilowatt hour. And today, new natural gas combined cycle, which can be built in about a year, would pencil out at around 5.5 cents per kilowatt hour. So you're looking at nuclear power, new nuclear plants that will produce power almost twice the cost of natural gas combined cycle. So that's a problem. That's why nuclear renaissance is failing. The only plants that are in construction are the Summer plant, and I believe the Vogtle plant is still going. And that's because those states can recover, or those utilities can recover all of their costs through the taxpayer. They're publicly owned utilities. So when we think about new nuclear plants, we have to figure out how to make nuclear power, at least in this country, not too much more expensive than natural gas. That's a very big challenge because there's going to be lots of natural gas for a long time. So, you want to have a good career in nuclear energy, put your heads together and think of a way to make it cheaper. So natural gas with frac gas is going to be cheap for a long time. The other issues of energy security, waste disposition, non-proliferation, those are contentious. They're political issues, but they're not showstoppers in terms of nuclear power right now. Its cost. So Fukushima was a major event. I don't know if any of you read that book by Nicholas Taleb called Black Swan. This fellow Taleb said, well, history is really composed of these unexpected disastrous events which change the course of history. And it's possible that the Fukushima is going to be one of those events which really changes energy, at least nuclear energy. We haven't seen the effects of all those changes yet. But I would want to classify Fukushima as a black swan. And in order for us to recover as an industry, we're going to have to do something different. It isn't going to be enough, just to go and review the safety design basis. We're going to have to think about something physical if we really want to recover from this particular black swan. So awareness of the financial risk associated with nuclear reactors, I think, is a major consequence. I think the bill for, in the case of Fukushima, for recovery, replacement, restitution, it's probably going to approach close to $1 trillion. The largest, utility in the world, TEPCO, is effectively reduced to receivership, through government support. And you have to imagine all these utilities out there, or power operators, look at the possibility of this kind of a consequence happening. You have to give them very strong assurances that that is not going to ever happen again. And as nuclear engineers, we have to assure that that will never happen again. Regulatory changes, well, so far, they're slow in coming. I think there's still a lot of study and work that has to be done to see what the regulatory changes are going to be, but there will be regulatory changes as a result of Fukushima. And most likely there'll be enhanced earthquake protection, improved availability of emergency power. And one of the things that people are looking at is an alternative to zircaloy cladding. And I'm going to talk a little bit about that today. Fukushima experienced 4 hydrogen explosions resulting from zircaloy reacting with water to produce hydrogen. And are there other materials that we could substitute zircaloy for and avoid that and make those reactors much safer? That would be the kind of physical change that we could make that could really help rescue nuclear power. So one of the ideas that made us look at an EM square type reactor, a fast reactor, a long burn core, was the notion of the amount of energy that's in depleted uranium and spent nuclear fuel. These are materials that are basically discarded materials. They're above ground. You don't have to mine them out of the ground. But if you could extract the fissionable energy from these materials, you would find that it's about 9 trillion barrels of oil. This is in barrels of oil equivalent, or BOE, you know, much greater than the energy we have in coal, oil, and natural gas in this country. This energy is like about 40 Saudi Arabias. You know, when it's here, all we have to do is use it effectively, and that's the idea we had in conceiving of an EM2 type reactor. So that amount of energy by itself could power the United States electrical needs for 300 years, assuming a 1% per year escalation in demand. And that's what we call energy security. So EM2 now looks like this here. This is in a below-grade containment. This is a fast reactor rated at about 500 megawatts thermal. It produces 240 megawatts electric through a closed helium gas turbine, direct gas turbine. Helium flows up through the core to the gas turbine. This is a high-speed gas turbine. It's a non-synchronous turbine. It introduces a whole new way of designing and controlling the plant, but the idea for increasing the speed is to get the size down, get the cost down for this reactor. Our criteria was that the vessel can be no larger than the largest vessel you can ship over road in the United States. That set the vessel diameter at about 4.5 meters. And then with that size, we looked at the most reactor we could cram into those vessels. And then that gave us the 240 megawatt electric size. This shows the safety cooling systems. These are passive heat exchangers, which by natural convection will cool the core, pressurized or depressurized, so that we have passive cooling. And this system will also sustain an ATWS event and shut itself down by the negative temperature coefficient, and that's because there's just so much uranium-238, and through the Doppler coefficient will shut itself down and stay safe. Yes?
So for the depressurized, you still contain pressure.
You'll have sufficient pressure contained in the containment to allow natural convection cooling. No, you can do it. Just I didn't tell you that this is normally held at 20 psig. That's the beauty of it, yeah. Yes. So this is a 30-year core, no refueling in 30 years, no shuffling. And I'll say just a little bit about how that is done. It burns spent LWR fuel, depleted uranium, or recycled EM2 fuel. This reactor, through its 30-year burn, most of the energy comes from uranium-238, which is converted to neptunium and plutonium-239. The waste stream, you know, with recycling is nearly all fission products. That has a major advantage in terms of the disposal. It is, you know, we talked about the high fuel utilization with multiple recycling and reduces proliferation risk. Passive safety, the efficiency is 48%. If you have a water source, or 44% with dry cooling.
On your completely removal and the normal Spinoff cooling system, the relative size of it, even if you're fully depressurized at atmospheric pressure, you can still use with that system?
You can passively, you would normally passively cool in a depressurized. There's circulators there just for maintenance when you need to reduce the temperature for refueling or reshuffling or inspection or whatever you had to do. This shows our what we envision in construction. We would build 2 modules at a time with a space so that you can build the second 2 while the first 2 are operating. You can start generating revenue and paying off the debt early before you start the construction of the next 2 modules. This fits in about a 15-acre site for these, which would produce about 1,000 megawatts. And what the reactor looks like, it's an upflow core. Helium is pressurized at 1900 psig. The core is in a hexagonal shape. These are hexagonal fuel bundles, rods. Just like any fast reactor, they're all hexagonal so that you can get a very tight pitch and very good heat transfer. And the coolant, the hot coolant goes to the turbine and returns the cold along the outside of the vessel and up through the core. All the control is from the reflector elements. Yes? Well, one of the major things is the large size of these cross ducts. So it has to be big enough for the cross ducts. And then we have then the joint with the top head that has to have enough space above the penetration here. And then this dished head then sets the rest of the size. That's as much as we could squeeze it. We can't take this down anymore. We can't take that down anymore. That's in the way. That's what sets the size of the top head. That's a very good question, though, because that translates into cost, and not just the cost of the vessel, but the containment and a lot of other things. So there's a great premium on the size of that top head. Oh, yeah, the control, the rotating drums. The shutdown rods are up here that go directly into the core. So that's the backup shutdown mechanism. And we are using vented fuel. I'll show you what that looks like. This is a fuel bundle. Initially, we're thinking about making what we call a tri-bundle. Since we don't have to refuel this except every 30 years, there's no need to think in terms of bundles that are easily removed. We can make them difficult to remove. So it's just cheaper to make them in a tri-bundle assembly. There are 91 hexes here, 91 rods per bundle. You ought to try designing a hex core sometime, and you find out with hexagons there are magic numbers that you can only work with. It's almost like a quantum core, and it turns out a little bit difficult to design, and you have to really work at it to find the magic number of rods and bundle sizes that will also give you the heat transfer that you need and enough uranium loading to put into the core. Yes. Well, originally we had a plate design. Our main concern was getting enough uranium into the core. In order to make this 30-year burn, we had to have 42 tons of uranium, some of which was enriched, some of which was depleted. And the only way and it also had to be porous, the fuel, in order for the fission gases to readily escape. And we determined we needed 40% porosity, and the only way we could get that much uranium in is with plates. Well, we basically proved to ourselves pretty quickly plates will never work because the fuel does swell, and we have to be able to react the swelling of the fuel against the clad so it'll collapse on itself. One nice thing about uranium monocarbide is it has a very high creep rate, and it doesn't take much restraining force to force the uranium carbide to collapse on itself. Well, so we really wanted rods, and we ended up reducing the porosity in order to compensate for the loss of volume by going to rods. And that seemed to work. And so it's a much nicer design overall, and just a much better choice.
What's the diameter of
The rods are, yeah, the rods are 21 millimeters outside diameter. Thickness of the clad is 1 millimeter. So the pellets are about 19 millimeters in diameter. The rod length the active rod length is 2.24 meters, and then we have additional length in there. It does have the The inner reflector is also in the rods. That's a beryllium carbide. And then there's some additional handling area. So these are close to 3 meters high.
And what's the pressure drop, helium pressure drop?
Helium pressure drop across the core, I believe, is around 8 psi.
How does that compare to like the other reactors?
Oh, I don't remember. Yeah, I'll show you. Oh, yeah. In order to make this work, we have to have really low leakage in this core. So this inner reflector is beryllium carbide. And it has an average of about 25 centimeters delta R, and then the cheaper graphite outer reflector.
What's that purple thing in the middle of your symbol?
Oh, that's just a grid. Yeah, for a spacer grid for holding the rods. The I wonder if I wrote that down here. No, I didn't. It's so you got a space between rods of about not quite 3 millimeters. The minimum space between rods is not quite 3 millimeters.
And you said it was 1.9 millimeters for the diameter?
That's the pellet diameter. With cladding, it's 21 millimeters.
Okay, so that's 20.
Yeah. I think in our ICNS paper from last year, May, or this year of May, gives all of those numbers in it, and I can send that to you, Tomas. So coming up with a grid design is always the main problem in designing a bundle, and that's an area, well, we're still working on it. We can make one, but assembling it is a real bear. So the spectrum is pretty close to a sodium spectrum. Sodium is a moderator in a sense. So this is slightly moderated because we do have some graphite there. But average neutron energy is about 100 keV. The conversion ratio at end of life is just a little bit above 1. So it is a real convert and burn type core. And it has very good neutron economy. The neutron utilization at the beginning of life is like 97%, meaning 97% of the neutrons either cause a fission or a conversion of U-238 to U-239, or to Pu-239. And I don't think any reactor that I'm aware of even comes close to that. I mean, like, I'm familiar with the MHR, and instead of 97%, that's about 60%. Annular cores are really leaky and not really good on neutron economy, and we really wanted to get away from that idea. So if you look at K effective over life, it goes above 30 years, never gets above 3%, and that enables us to control from the reflector area. That's a really critical feature of this reactor, and it takes a lot of work in designing the core to get this kind of behavior. And you can see the effect of, you're producing a plutonium, but you're producing fission products which just kind of hold this steady over time. The end of life plutonium is not quite 3 tons, so there's a lot of plutonium in there left. But it's about equal to the amount of fission fissile material that you started with, so you have almost a constant amount of fissile material.
Is that for reprocessing?
Yes, and I'll talk a little bit about how you recycle this core, which I think is an advantage. It's 15%. Yeah. You have a lot of options. Now, the way you design these kind of cores, and I think you're all familiar with Bill Gates's concept, TerraPower, where he puts a starter material. He calls it an igniter. I think this concept was proposed by Teller, and Professor Sakamoto is, of course, the pioneer in this idea of long burn cores. But you begin with a starter, a fissile material. In our case, it's about an average of 12% enriched LEU on the first core. And this is not the shape of the starter. It took us months and months and months to figure out the shape that would actually work. And after doing that, we were able to then get a long burn with a very flat reactivity profile. But I can tell you that the amount of fissile material is about half the core, and the amount of fertile material is half the core. And the fertile, yes?
So for the startup fuel, what's the amount of enrichment work that's needed compared to, say, starting up a light water reactor with one donor product of the same color?
You mean the amount of SWUs?
I'm just because you need to go critical, you probably need a bit higher fissile loading, but it's a higher power density
Yeah.
also, right? So I'm just curious about sort of the startup capital cost for the fuel.
Yeah, that's an important fact because of the 30-year core, and that core is a capital cost in this case. And it is a major cost compared to a light water reactor because of the fact that you're loading it with over 22 tons of average of 12% enriched material, and the SWU cost is very, very high. I just off the top of my head, I can't tell you what it is. I have, you know, the spreadsheet for that calculation, but I'll get you that number.
How does it compare with the 30 years fuel cost?
Oh, it's cheaper. Obviously, the 30-year cost of this core, the fuel over 30 years, is cheaper than, yes, yes. So, when you burn it for 30 years, what happens? That fissile starter, that burns out pretty quick. And most of your energy comes from the Pu-239 over time. So most of the energy comes from waste, from discarded, depleted uranium or spent nuclear fuel or anything that has a lot of U-238 in it. And that's the idea here, that we can take discarded materials. We don't have to worry about how to dispose of these wastes. It's valuable fuel. Let's use it. And so that's the notion here. But when you have a 30-year core, you build up a lot of pressure inside the rods from the fission gases. And if you decided that you want to make a rod to contain that pressure, you just couldn't do it. You have to vent the fuel. And so right off the bat, we had to make a decision to vent the fuel. Now, lots of reactors have been built with vented fuels. The British Magnox and AGRs were all vented. Our first reactor at General Atomics, the Peach Bottom reactor, was a vented fuel design. Worked fine. We think we know how to do it. And so we decided to vent the fuel. On this particular design, this shows the fuel rods. The fuel is actually an annular pellet. The fission gases travel up, turn around, and then come down a central downcomer, and then connects to a distribution network at the bottom, in the cold bottom of the core. We spent about 2 weeks trying to decide whether we need to vent up or down, and we decided we had to vent in the upward direction because if debris fell down, we wanted to be sure that we didn't block the pathway of the gas. And so we decided to vent up. It turns around in a manifold at the top, and at the top in that pressed silicon carbide manifold, and then vents in the downward direction. So that's the vent design. Yeah, these are basically fission gases, but with a vented core, we don't have to have hermetic fuel cladding. We can allow leakage, and you know, cracks and stuff are going to occur. There's going to be pinholes, especially with silicon carbide composite. So we allow quite a bit of helium leakage. We separate it out in the helium purification system and return it.
So, but that's mixed with the coolant, the fission gas.
Inside the rods only. They do not get into the primary system. Is that clear?
No.
All right. Here's the fuel rod. Fission gases go to the central annulus. And see this gray area? That's helium coolant. Okay? So the cladding prevents the gases from going out. And it then goes up to the manifold and then comes down a downcomer through a separate pipe out. It never touches the helium coolant. Now, helium can leak in because this pressure is lower than this pressure. So helium can leak in. And if there are any really interested students, one really fun thing to do is assume you have a pinhole in your clad. What pressure does it take to suppress diffusion against the inflow of helium? So that if you ever want to do a diffusion calculation, that's a fun one to do. So anyways, the fuel cycle is you have an LEU starter to begin with, and you have used nuclear fuel or depleted uranium or anything, and you run it for 30 years. You take the discharge. You take out about 60% of the fission products. You don't have to take them all out. And then you put this back into the reactor after refabricating it and add some more used nuclear fuel, and you can go again and again and again doing this. Now, if you use used nuclear fuel, you don't have to take the fission products out at all. Because this is a fast reactor, those fission products have negligible negative reactivity, and you can just, all you have to do is just refabricate that fuel and put it in the reactor. No, that's the interesting thing, because this fuel has plutonium in it, and it compensates for the negative value of the fission products in a fast spectrum.
But it's only 1% plutonium.
Yeah. And then it has about 1.5% uranium, 235. Right. And it has about 5% fission products, which are not worth an awful lot in the fast spectrum.
Is that used fuel like water reactor fuel? Is that what you mean by
Yes, light water reactor fuel.
How do you have to change the oxide to a carbide?
Right. Let's talk about that for a second. So what do you do? How do you do this? We use what's called an AROX process, developed by Atomics International originally. Work was done on it by the Koreans. They call it a Dupik process, and they actually built a Dupik plant for converting light water reactor fuel into CANDU fuel. And also work was done on this by Oak Ridge, and they called it an Oriox process. But it's all basically the same thing. So what do? You take an LWR fuel rod, you pierce the clad, and then you subject it to alternate oxidizing and reducing environments, which converts U-230 to UO2 to UO3 to UO2. So you go through volume expansions and contractions. This pulverizes the material to a very fine powder after 3 cycles of this, and you just literally pour it out of the fuel rod. That was always a problem, how you can get the pellets to not stick to the zircaloy cladding. But they found this works quite nicely. And so as an oxide, UO2, we take it, dissolve it in acid, and then in a sol gel process in which we can accommodate particles and other stuff and still create a gel particle. In fact, we add carbon to the gel particle. We then make the particles and go through a succession of heating. In the last step, we heat it to about 1700 degrees C, and we convert the oxide to a monocarbide. And we can control the stoichiometry very precisely by how much carbon we put into the original sol. And after a lot of work, about a year's work, we've been able to figure out just exactly how to add that carbon so that we get a very carefully controlled stoichiometry.
Has this been done in the lab? Actually,
Oh yeah. We're making we're making it now, and I'll show you pictures of our sol gel column and the material that we're making now. Yeah. Yes. Well, the idea was to try to get as long a burn as we could within the confines of a certain size that was set by the vessel. And it turned out 30 years was as much as we could get and still get a very uniform reactivity curve for that length of time. Yeah. And at the end of 30 years, the value, you've depleted, 15% of your material, and you've also built up fission products, and you just can't make it go any longer. So that determines 30 years. There's another hand. Anybody else? I want to make sure I answer all your questions.
Now you have to do all that milling and blending and fabrication in highly radioactive materials. The fission products are still there.
The fission products are still here, and yes, you have to do that remotely. So this is a very fine powder, but you may want to blend it with other materials. So I mean, I don't think this is rocket science. They do this in reprocessing. They have machines for doing these things remotely, and I don't think that is very difficult. Putting it into a silicon carbide rod is going to be more of a challenge. But making the pellets, I don't believe is going to be that difficult. And we can do essentially the same thing with recycling our own fuel by this Aerox process, but there's one feature here is that we do need to take out about 60% of the fission products, and it has to be somewhat pretty well distributed over all the different species. And so we have to add other gases besides just oxygen and hydrogen to try to extract those fission products out in a gaseous process. And the way we want to do this is only to extract fission products, but not touch the heavy metals. So it becomes a pretty tricky chemistry because some of the fission products, like strontium, for example, have chemistry similar to uranium. So we're not completely there yet. I don't want to say this is a done deal, but there's a lot of people working on this, and we work closely with Ken Chawinski to work on ways of extracting those fission gases. But I think that's a very good area for research, is looking at how can you extract fission products without touching the metal. I mean, that's really a proliferation-proof way of recycling. So I don't have to tell you that, if this all works and if we're able to recycle, the waste products here are basically fission products. And except for a couple of isotopes, the fission products, you could hold them in your hands after about 300 years. You can't eat it, though. Don't eat it. So we need a repository. We're going to need that. Maybe it doesn't have to be a Yucca Mountain, but maybe you only need one and not a huge number if you did this. And so this shows how we make fuel. We make urinal nitrate gel particles in the sol gel column there. You can see they're black. We put some secret sauce in there that has carbon material in it. Then you go through a very carefully controlled drying, calcining, and carburization stage. And at this high temperature furnace, then we convert the oxide to monocarbon. It's not monocarbide. We have to add a little extra carbon in there because fission products like to grab carbon. And we don't want it grabbing carbon from the silicon carbide composite clad. So we have to put a little extra carbon there to be sure that we passivate those fission products. So we make these UC kernels, and then we sinter them. This just shows a sintering experiment in which we do it by pressure. We actually want to make annular particles, and we have to guarantee that all these particles have really good contact thermally, so we have good thermal conductivity. So we're investing in spark discharge sintering processes to be able to do this, so that through a large electronic spark, we weld all these particles together and get good thermal contact. So this is a very innovative way of sintering material that we're working on. And then we built this silicon carbide facility for making silicon carbide by a gaseous infiltration process, which you decompose methyl trichloro silane. There's two furnaces here. This is what we call ICVI, meaning isobaric chemical vapor infiltration, and the molecules of MTS, methyl trichlorosilane, find their way into the weave of silicon carbide fibers and then decompose and leave silicon carbide, and hydrochloric acid has to come away. Well, it takes about 300 hours to make about 1 millimeter of material by that method, and that's a really costly way. So we've been looking at ways to make it go faster. And in this furnace here, we now do that by what's called FCVI, or force flow CVI, to try to really accelerate the way in which we can build up silicon carbide and get that cost way down. And here's the problem. I mean, silicon carbide fibers cost around $10,000 a kilogram. And if you do it by this process, you add another 10,000. So you've got a material that costs $20,000 a kilogram. Well, that's pretty expensive material, and we need to cut that down by a factor of 10. And that's where most of our work is going in right now, to get that cost down. We have other magic ways of accelerating that as well. And this, these are the kind of things, this is our day in and day out product, just making coupons, varying parameters, studying the properties until we can find the magic formula of making material quick with the kind of strength and impermeability that we would like to have in this material. That's a good question. No, what do we want in this material? We want a material that has good strength at very high temperatures. The gas temperature is around 850 C at the peak. The peak clad temperature is around 1100 degrees C. But it experiences over 30 years about 300 dPa in damage. And silicon carbide, beta silicon carbide, appears to be one of those materials that's self-healing and has the potential, to get way up there in dPa. Like there are other materials, ODS and HTS, also seem to be self-healing and have this capability. One of the downsides of doing this is you have to prove it, which means you have to accumulate that much damage in the material. And that's a whole science in itself as to how you can do this economically, and I won't go into that. But that's the reason. You want a radiation-tolerant material. Excuse me for looking at my watch. I'm going to move along here pretty quickly. So anyways, we do a lot of different work. One of the things on the turbine, by the way, is the high-speed turbine, so we can get the size of this down. You have to invert the frequency as a result. And we just happen to have a product that can take variable input and invert it to line frequency at 99%. And so now it gives a whole amount of freedom now in how we choose our turbine and how we design the reactor, because we're not constrained to make a whole reactor control system to produce a synchronous signal. And that's, I'll tell you, there's like many theses in this, and we do have a young man from UCSD is doing his thesis on designing the control system that could take a variable input. And we're actually building the generator at General Atomics at a 65 megawatt size. And this is also interesting because we chose to use a permanent magnet rotor, because you can get another point or two of efficiency if you don't have a wound rotor with an exciter. 1 point in efficiency for a reactor of this size is worth $1 billion in revenue. So efficiency matters. I'm going to just kind of skip along here, because I said, well, gee, how do we pay for this? And one of the major areas is silicon carbide, and being able to make it cheap, be able to join it, and all the things that are going with it. And this is one of the areas we spent some time. I mean, even though it's been new for us, we're starting to make some headway. And because of Fukushima, there's a lot of focus on silicon carbide for cladding, for light water reactors, because it turns out that silicon carbide reactions with water are several orders of magnitude slower than zircaloy. So you can effectively say that generation of hydrogen in an accident condition will not occur. Now, like I say, that could be a game-changing idea if we could make cladding cheap enough. And that's something we're really geared to do right now. We've committed, and we're trying to do this.
Can we easily join an end cap to the top of
Well,
I mean, you can't weld it stuff. So,
there are many ways that people have looked at to join silicon carbide to silicon carbide, and there's been ways in which use metal materials, but they don't stand up to irradiation very well. What we have been able to achieve is a beta silicon carbide joint, where we use only beta silicon carbide material as the weld material, and within a few hours, we're able to produce a hermetic joint that is only beta silicon carbide that will sustain the radiation. That's one of the things that we claim as an achievement in our little program, and this has gotten some attention right now.
there's no pressure buildup in the rod because you're venting
Right.
all of the fission gas.
Yeah, but in a light water reactor, that's a different story. Light water reactor clad is more difficult because you do have to retain the pressure, and you do have to retain the tritium, and it must be hermetic.
But in the EM2 fuel, you have perfect fuel clad in contact. There's no gap. Right? You let the silicon carbide.
Yeah. There's no gap. Yeah.
There's no
Right.
fuel cladding gap.
Yeah.
So how does the fission gas get out to the top to be vented?
It's an annular pellet. Remember I said it was an annular pellet. Oh, yes. At temperature, the silicon carbide composite's as strong as the zircaloy. Well, you call it quasi-ductile. When you make the composite with fibers infiltrated with material, it is able to transfer the loads to the fiber, and you get a little bit of ductility, but a great deal of fracture toughness, such that the fracture toughness of the composite is very close to the zircaloy, but you give up a little strength when you do that. But in the end, the silicon carbide composite is as strong as the zircaloy, and has as good and when I say as good of, within a 70%, 80% of the fracture toughness of zircaloy.
But you do get fuel swelling, so you get
Right.
that's cladding out.
Right. So that fuel.
Creep,
Yeah. No, that is a problem that we have to solve, and have not solved that. And that the UO2 pellet will not give like our UC pellet, and it has to. It will swell. The silicon carbide has negligible creep, and so we have to think of a way in which we can accommodate that swelling of the UO2. And so one way is to make an annular pellet, which is done in India. They do that, for example. They make annular UO2 pellets.
the EM2 reactor fuel. How do you accommodate the swelling of the carbon?
Well, in that case, the UC has a very high creep rate, and it'll react against the silicon carbide composite clad and collapse on itself because of the porosity that we put into the fuel. Well, I mean, you make the composite by making a fiber preform. You do put a small layer of pyrocarbon around each fiber so that you get slip between the fiber and the matrix. That's very important in fracture toughness. Then you infiltrate it, and ultimately you make tubes. And we're making tubes. They're a little bit crude right now, but we're getting better at it. So, and in a light water reactor, you've got to make the grids, the fuel clad, and the end caps all out of silicon carbide. And in a BWR, you also have to make these shrouds out of silicon carbide. So in Fukushima, these shrouds contributed a great deal to the hydrogen production that caused the explosions. And so one of the things we're doing here, you take a normal PWR rod, which is about 9.5 millimeters in diameter. It turns out to make the silicon carbide, it's going to have a thicker cladding than the zircaloy. And if you use the same geometry, it's going to squeeze the amount of UO2. And in fact, you'll lose about 20% of the fuel volume. Well, that's kind of interesting because it turns out that the cross-section of silicon carbide is half of what the zircaloy is. And so you gain a little reactivity by going to the silicon carbide, and you only have to increase the enrichment here by about 0.6% in order to get the same lifetime as the O2. And since you're buying 20% less, the fuel cost for this will actually be lower than this here. So I'm not going to go through all of this because the time is getting late. What happens in an accident? You know, zircaloy really reacts fast with water. And this shows that this is reaction time in days, and this is the amount of hydrogen generated per meter of rod surface. And at 1100 degrees, basically after about 1.5 days, you've consumed all of the zircaloy. At 1400 degrees C, after about an hour, you've consumed all of the zircaloy. Somewhere in between here, the heat from this reaction outpaces the heat from the afterheat of the reactor, and so it's self-sustaining. With silicon carbide, well, it does react with water, but very, very slowly at these temperatures. And you can see after a couple of days, you know, less than 1% of the silicon carbide would be consumed at 1400 degrees C. So that's the safety basis for this. And if you look at the strength comparisons, this assumes that you design both a silicon carbide rod and a zircaloy rod, you know, for the same strength at operating temperature. But as temperature goes up, silicon carbide, you know, doesn't lose any strength, but the zircaloy rapidly loses strength. So there's many design basis accidents that would not cause fuel failure if you use silicon carbide. So that's the incentive. The negative part is, can we get the cost down? And we solve the problem with oxide swelling. I think we can. You know, we've got about 3 more minutes, and I think I'm not going to, I can go into some other things, but if you got some questions, Tomas?
Of course, the questions. But first, let's,
Do you have a plan to qualify silicon carbide?
Yes, and that takes a long time because we first do rodlets in a reactor like ATR. Then you've got to do a full rod, and then you've got to assume that your first try isn't going to work, and you're going to have to do another one, and that's another 4 years. So it does take a long time to do the qualification.
And then is General Atomics going to be the cladding center?
I think we see ourselves as just supplying silicon carbide clad, just like a zircaloy fabricator would do, and we would sell that to the existing field vendors. Yes, sir.
Yeah, answering to Mr. Peterson's question about differentialization,
Yes.
you say that kind of accident never happened before.
Oh, well, no, it certainly can happen.
Oh, yeah, but maybe the effect is very slow. Is the whole system is contained in physiology, or I think
Well, there is a containment. All of the coolant is contained in the containment. And the transient is slow because of the huge mass of the core. It does go slowly.
like same as the conventional or inherent reactor, modular high-temperature reactor.
Not quite the same, but close.
In that case, yeah, graphite amount is so much.
Yeah.
And but this reactor only fuel and cladding in the core.
Yeah.
So I just wonder about the capacity of heat.
Well, I would, if you would give me your card, I would send you a paper on this that shows the numbers so you can validate for yourself.
And for this case, probably we have to consider about great change in this kind of case. Finally, the temperature just go over the limit, maybe fuel temperature. Then, but the time this kind of thing happens.
yeah.
It's very long, yes.
So yeah, maybe we should estimate the so-called break period or time. Yeah.
I would very much like someone else to do these transients as well as us. It helps us, to be able to stand up with a straight face and claim these nice passive features.
I can understand.
Yeah. So I would be very happy to share with you some of the data if you can convince a very able student to reproduce it. That would be very nice.
One or two more questions? David?
So instead of taking that, please, you said that is it active or passive? So it vents out and then pull it down?
Well, of course, it flows by a negative pressure coefficient that's created by a helium purification system that is producing that negative but that's outside the reactor.
Okay, and you said that the top part was silicon carbide manifold.
Yes, it's just the top of the fuel bundle has manifold passages in it. You do it by pressing, hot pressing silicon carbide or reaction centering silicon carbide to that with those shapes in it. Yes. Well, other people have made permanent magnet motors at a small size. The highest permanent magnet motor was about a megawatt. Now we're taking this to a whole new regime at 65 megawatts for the generator that we're building. And we think there might be, again, a whole market just for generators with permanent magnets. As I said, you get an extra point of efficiency or two from your generator, that is worth a lot of money. So that's something we're working on. Yes.
One more question. The silicon carbide reaction with water. Have you looked at whether you generate silane?
Do we generate silane? Oh, no, it's silicon dioxide that you make and carbon dioxide. Oh, no, wait, there's an H2, I think I have the, yeah. Here, this is the reaction right here. That before makes CO2, SiO2, and 4H. That is the reaction.
But that reaction could also produce SiO4.
I would guess I'd have to see in an equilibrium chart where that might occur. I'm not an expert on that. Yeah.
Okay.
Okay.
We went over just a little bit. It's time for us to thank Bob again. A very good job.
You're a good audience and a lot of fun. Thank you.
Thank you.